Can everybody see the full screen with the slides? Cool, cool. All right. So thank you everybody for coming to this week's GSC seminar. Today we're having Rebecca Kerfis. Just a quick reminder, this is our current leadership team. Roshan and I are the current chairs. Our publicity team consists of Reza, Rajmohan, this is an older one, and Avinash. And then we also have Anirban, Emmanuel, Rodney, Nazli, Schwabnil, and Andrew, and also Fulani, who's not on here because I don't have his headshot yet. And our mentors are Farouk and also Robert Rucker, who's a close mentor on the team. For anyone who wishes to attend our leadership meetings, we have them regularly on Fridays at 4 p.m. They're done over Zoom currently. And we are happy to move the schedule if more people would like to attend the meeting but can't attend the Friday one. If you would like to join us on Engage, then we have our QR code here. Alternatively, you can message Roshan or I, and we can get you involved in the GSC. Another reminder, we have our Facebook page that broadcasts all of our events and has links to the talks once they're recorded and put up on our YouTube page. So if you have to duck out early, we will have this put up later as soon as it's done. And then we have a few more events coming up. Next Thursday, we have research experience in the industrial sector for those of you who are more interested in looking more at applied research. And then the week after that, we have a lecture on designing for patentability. So with that, I'm going to go ahead and introduce our speaker, Rebecca Kerfis. She is at the Oak Ridge National Laboratory and a PhD candidate in mechanical engineering at the Massachusetts Institute of Technology. So go ahead and take it away, Rebecca.
Great, thank you so much. Let me just figure out screen sharing and then I will take it away. All right, can everyone see?
Yep, you're good.
Perfect. So I actually have two different bodies of research that I can present here, and I'm going to start actually in the middle. So this is actually the wrong slide. I apologize. So I'm going to start with what I find to be the more exciting for discussion content because it's my current PhD research. So I think that this will provide a much more exciting discussion. And then if any of you want to stay for sort of a more completed body of research that I did on thermal modeling of the polymer extrusion process for prediction of interlayer weld quality in large-scale polymer extrusion, which is kind of a mouthful, I'm also happy to discuss that as well. But for now, I'll start with this body of work.
See?
Hello? Okay. As Rachel said, my name is Rebecca Kerfis. I am in a unique and very exciting position of being both a PhD candidate at MIT and also a staff researcher at Oak Ridge National Laboratory, which is in Oak Ridge, Tennessee. It's a really exciting position for me because I get to basically use a national laboratory as my grad lab, which has given me a lot of exciting opportunities to do things like use a lot of different metrology and characterization equipment and larger, more commercial systems, which has been very exciting for me. And I'm going to present to you today the work that I've done so far on directed energy deposition on polymer substrates. So a little bit of an introduction for those of you who don't know as much about additive manufacturing. Additive manufacturing as a general process is this idea of selectively depositing material to build up a component versus the more traditional subtractive manufacturing where you start with a block of material and you take away the parts of the material that you don't want to create your shape. Additive manufacturing, as I'm sure you all have heard, is very exciting for lots of reasons because of its incredible flexibility. So it's not super fast and it's higher cost than a lot of manufacturing processes, but you can make really complex and organic looking shapes, which has been very intriguing for many different industries. Metal additive manufacturing is even more exciting because you can start making functional complex geometries. So parts that you can use in airplanes or in cars or in the mold and die industries. There's a couple of different forms of metal additive manufacturing, and the specific process that I work with for my research is directed energy deposition, or DED. DED is the process of having some kind of power source. So it's usually either an electric arc or laser beam, and some kind of feedstock that is fed directly into that source to melt it and then deposit it on a surface selectively, layer by layer, as is traditional with additive manufacturing. The specific system that I work with is a blown powder DED system. So it uses a laser beam to melt powder that is blown directly into the path of the laser, which is then deposited onto the substrate beneath the laser. There's also wire-fed DED, as you can see in this other image, where you basically take a wire and feed it in instead of blown powder. Blown powder is particularly exciting because it enables things like functionally graded materials, so you can change powder composition on the fly, which is pretty exciting. I mean, you can shift from one material to another in a single component. But of course, I've spent just a couple of minutes talking about how DED is really great. Like any process, it has its limitations. And because DED uses a much larger bead, so it's a pretty large scale metal process. I mean, you can make parts that are on the order of a meter large. It's very, very difficult to create overhangs and bridges, more so than with other processes, because the bead that you're using is much larger and much heavier. So you're really restrained in the steepness of your overhangs, the length of your bridges, and therefore in the overall possible complexity of your geometries. So the general rule of thumb is that you really can't print anything greater than 20 degrees as an overhang. There have been some strategies to try and mitigate this and to problem solve this. There has been some minimal work in support structures in DED, so similar to support structures that you might see in plastic 3D printing, desktop 3D printing, but they're much more difficult to remove and much more difficult to design in the first place. Again, because your bead is so large, it's much trickier to machine it off at the end. It's much trickier to get the lattice type support structure to support the weight of your bead. So they're really not frequently used. I've been at Oak Ridge over a year now, and we have, say, 3 DED systems, and I've never seen a part printed with a support structure. Another option is to use a 5-axis system. So basically enabling you to rotate and reorient your parts so that, looking at your part, it is a steep overhang, but when it's printing in the machine, the part isn't seeing it as a steep overhang because of reorientation. But 5-axis machines, I don't know if any of you guys have looked into the cost of machine tools, can usually add 1 or 2 zeros to the end of your price for those. And you still can't print things like bridges. So you can't have a gap that you print over with your metal. And of course, the final option is always to redesign your part entirely or to use another process. So the proposal of my research is that we can use a different material, such as a polymer or a polymer composite, to support our metal bead during the DED process, enabling geometries like bridges and steep overhangs. If this is possible, it would really expand the DED design space and enable even more functionality of components for industries like aerospace and the mold and die industry and the oil and gas industry. So the ability to expand this DED design space is really the goal of this research. But of course, first we have to see if it's feasible at all. So a little bit about the system that I'm using for this. The system actually inspired my research because it is a hybrid system, which as a general rule includes 2 or more kinds of manufacturing processes. Generally up to this point, it's been metal additive manufacturing, so some kind of DED process in combination with machining to provide both the flexibility of additive manufacturing with the precision and good surface finishes of machining. The system that I'm working with, which is a Haas CNC machine tool that was modified by a company called Hybrid Manufacturing Technologies, or HMT, to be a hybrid system, actually includes both the blown powder DED that I mentioned earlier and polymer extrusion. So we have the capacity to print something out of polymer and then come back and print with metal on top of it. That's never really been done before. It doesn't sound like a good idea when you first introduce it because the melting and degradation temperatures of polymers tend to be much lower than the melting temperatures of most metals. But we wanted to investigate the feasibility of integrating these two processes, this polymer extrusion along with the blown powder DED. Before we did that, I did a little bit of a dive into sort of polymer material science. And one thing that was very encouraging for this body of research is the idea of ablative polymers. So they actually do make a category of polymers that are designed to survive in extreme environments. They're generally used on things like spacecraft reentry. It's unreasonable to expect any polymer exposed to very high temperatures, things like being blasted with a laser or getting molten metal, dumped on them, without some kind of degradation. But the goal with ablative polymers and what has been achieved by some of these polymers is that you have a thin layer that degrades of the polymer, and the degradation of that layer results in some kind of shield that protects the bulk of the polymer from further degradation. So basically you have a char, usually in traditional ablative polymers, it's made mostly of carbon, which can resist much higher temperatures than the original polymer. And that carbon char will protect the bulk polymer from the rest of the heat. Unfortunately, the traditional ablative polymers tend to not be very printable. They tend to be thermosets, which are polymers that are created via a chemical reaction. So generally, think of something like super glue. You squeeze it out of the tube, it reacts, it solidifies, and you cannot process it again. Versus thermoplastics, which are the material generally used for polymer 3D printing, which are the types of materials that can be heated up to soften them, extruded, printed, formed, and then reheated up again. So you can cycle them through heat. Those two are, the Venn diagram of those two doesn't really overlap. So what we needed to do was see if any of the polymers that are readily available for the extrusion printing that we have on our system could act in this ablative manner. So what we were looking for was to create kind of a pseudo-ablative effect with a non-traditional ablative polymer, a non-ablative polymer. So we investigated the idea of filled polymers. So several types of polymers that are printed on, especially large-scale polymer extrusion systems, are polymers like ABS that are filled with things like glass fibers and carbon fibers. The reason that those were introduced in the first place was because these fibers actually mitigate a lot of the warping issues seen with larger scale printing. But we hypothesized that by using these polymers as our support structures in the DED process, these fibers would actually protect the bulk polymer from the thermal effects of the DED process. The idea behind this is that you have a polymer that's embedded with a bunch of chopped fibers, whether they be carbon fibers or glass fibers. When you expose your polymer to both the laser and to the molten metal, you do degrade a thin layer of polymer, say ABS or nylon. But by the degradation of that polymer, you expose a layer of previously embedded fibers that can resist much higher temperatures than the polymer on its own. Once you have these exposed fibers, they can shield the bulk of the polymer from the thermal effects of the process. So that was our hypothesis. And then we got in and ran some trials. So this is actually the first one that I ran, which is a stainless steel pass at 100 watts on the system with carbon fiber ABS as a substrate. So I'll just play that again. So you can see that what we get, I don't know if I can pause it halfway through. Maybe not. What we get is a lot of flaring and sparking, but we actually don't get any, I've been told to call them thermal excursions by the lab for safety purposes. So we don't actually see anything that sparks a lot of safety concern, although we do see more flaring than traditional metal on metal deposition. And you can see here in this image that the substrate actually did survive with minimal geometric integrity loss, which is exciting. And the bulk of it didn't burn and didn't melt. So our next step was to set up some high-speed imaging to sort of see if we can figure out what's happening in the process and to see if we can confirm any of our hypotheses about what's going on. So you can see in this video that we're definitely getting a lot of flaring at the point at which the laser is hitting the polymer. You can also see that the metal is not wetting the material very well. I don't know if any of you guys have a lot of experience with carbon fibers, but metal does not tend to wet carbon fiber very well. So this makes sense. And a key observation here is that you can see a lot of smoke coming off. So you can see almost this plume coming off of the polymer as it's interacting with the DED process, which indicates that our hypothesis about a thin layer of polymer degrading is correct, because that smoke, that residue, is an indication that the polymer is burning off and creating some kind of gaseous residue. But of course, what we wanted to see after that is if our hypothesis about the exposed carbon fibers was accurate as well. So this is a series of experiments I did at varying powers. But the point of these is that you can actually see the exposed carbon fibers under the microscope when you image them, which indicates that not only was our hypothesis about the degradation of a thin layer of polymer correct, but our hypothesis that the exposed carbon fibers as a result of that are what's protecting this polymer from further thermal degradation. I mean, you can also see here that with increased power, you get increased residue. So you get almost like a tail of residue that's caused by the smoke. And you can also see it as sort of blackened material on the metal itself. So this is very exciting. It does confirm our hypothesis. However, these aren't fully deposited beads. So basically what we have here is a spray of metal on top of carbon fibers. Because as I mentioned earlier, metal does not wet carbon fibers well at all. So the next step was to determine if we could achieve a solid bead. So we just started doing multiple passes. When we tried 2 passes, we did get more coalescence of the metal into metal balls and almost a resemblance of a bead, but definitely not a full bead. And then once we hit 3 layers, we actually did get a fully deposited bead. It is easily removed, which is very exciting because the goal of this research is to investigate support structures. So the fact that the polymer comes easily off of the metal is very exciting. On the flip side, you can see that there are actually carbon fibers embedded in the bottom of the metal bead, which is a little less exciting. It indicates to us that the first perhaps millimeter or 2 of any metal component that's printed on top of a polymer substrate might not have the same integrity, might not have the same material properties as the bulk component itself. So there's definitely work to be done in optimizing those parameters and making sure that we are building up a metal component that is still functional. And then maybe it won't go to the next slide. There we go. And then another test that I did with the carbon fiber ABS was just to see what happens when you try and stack multiple layers. So up to this point, I've been sort of looking at the short-term effects of the DED process on the polymer, basically determining whether or not the polymer will survive being exposed to a laser at 100 watts and being exposed to molten metal. So what will the polymer do on the order of microseconds to milliseconds in response to this process? But I also wanted to see what happens to the polymer longer term, because what you have if you're building up layers is the polymer is no longer being exposed to the laser directly, because the laser is now on top of this deposited metal. But you do have a component that's a couple hundred degrees Celsius that's resting on top of your polymer, which has a melting point of a couple of hundred of degrees Celsius. So here I have a video of the process. You can see that initially there's still that pretty intense flaring, but that decreases over time as you start hitting the as you stop hitting the polymer directly with the laser. You can see that the metal component remains hot, so it's pretty red hot in this image, but you can see that you are getting a buildup of material over time. And as you can see from this final image of the single bead wall that I built up, you don't see much degradation of the polymer with respect to melting. So this is still a pretty solid block of polymer that you have at the end of this experiment. So this was really promising because we now know that we can build up enough layers of metal that at this point, even if the polymer were to start melting or to start degrading further, we would still be able to build up enough metal to support itself before the polymer is so negatively affected by the DED process that it's no longer useful as a support structure. So my next step was to test a variety of polymers. So I'd worked with carbon fiber ABS, but Oak Ridge has a bunch of different polymers that are available for testing. So I tested a couple of different filled polymers. I wanted to test glass fiber filled, along with some unfilled polymers, just for kind of a comparison. So here I'll show the glass fiber polymers. I did an ABS and a nylon, and both of them had more deposition of metal than the carbon fiber ABS because you're working with glass fibers instead of carbon fibers. Both of them still had that flaring from the degradation of the material. Someone unmuted. All right. And then I also tested I tested one unfilled PLA and one PLA that was filled with wood flour. I was a little nervous about that one, potentially having a thermal excursion, but it surprisingly didn't. We actually got less flaring with these two tests than with the ABS, which indicated that we're actually seeing more melting of the material than degradation of the material. And we also got more of an embedding of the feedstock powder than melting and resolidification as a bead, which was very interesting. So it doesn't really provide that same ablative effect of exposing something that could protect the bulk polymer. So this was less promising as a feedstock material. And then I also tried it with a high temperature material called PEEK, which I expected to perform better, but was actually pretty surprised that it had a lot of flaring, which is generally a little bit less safe. And it also, the material tended to expand. So basically the exposure to the laser and to the molten material resulted in such a transformation of the polymer that it actually expanded and shifted the metal deposition. So this was actually the least promising of the polymers as a support structure, which was definitely a very interesting result. And then I also did high-speed imaging of all of these materials. I'll just play them all at once so you can kind of see them. And the high-speed images serve to further back up the hypothesis that with these filled polymers, so the three polymers on top of this slide, you see degradation, so you see more significant flaring and more significant smoke as residue from this degradation. versus the two polymers on the bottom, which are not fiber filled, which have more of a melting of the polymer, embedding of that feedstock powder in the molten polymer, and then resolidification of the polymer. A lot of videos. So the next steps for this research space are to, one, quantify the effects of the laser on these various polymers. So I'm planning on cross-sectioning all of those single bead samples and measuring the laser affected zone in those areas. And also to quantify a new DED design space. So printing a series of overhangs and bridges and determining what geometries are now enabled by these supports that were not previously accessible by our systems. So that is sort of a semi-brief introduction to the research that I'm currently working on, and I'm happy to take any questions now.
Thank you so much, Rebecca. Does anyone have any questions or conversations that they'd like to have with her? Also, just a quick reminder, we did post a Google form for you to fill out for attendance so that we can have that. So just a reminder to check the chat for that. But anyone with questions is welcome to ask them at this point.
Rebecca, are you going to also talk about some of your metal work, or this was going to be the conversation for today?
I'm happy to have a longer conversation here. I do have a different body of work if I end up having time at the end. But this is the work that I'm a little bit more excited about because it's my current research.
Right.
I think Andrew has a question.
Yeah, thank you. I just wanted to confirm the support material you're looking at, is it just polymers, or you're also looking at, because I saw somewhere wood flour for the PLA. Is that some kind of polymer?
Yeah, so they are, I did test some pure polymers. So I tested like neat PLA, which is just a polymer. And then I tested some polymer composites. So usually 10 to 20% of some kind of filler material, such as glass fiber, carbon fiber, or in that case of the material you're talking about, it was a wood flour, which isn't really a fiber. I just wanted to see the effect of the wood flour versus a neat or unfilled PLA.
Oh, okay. And then the last question I have, so like from the different materials that you tested on, both at MIT and at Oak Ridge, like, is there a way to tell which gave the best performance and which you were considering to do the further tests on, based on the comparisons, maybe some kind of comparisons you've done with the different materials? Yeah,
that's a great question. So one of the things I'm looking at is the laser affected area. So I didn't include it because I haven't finished all of the samples yet, but one of the things I'm doing is cross-sectioning these samples and looking at the YZ plane of each section and determining how much of the polymer is degraded by the laser. So you get basically a channel that it no longer has polymer in it. And also the laser affected area. So you can see an area in the polymer that's affected by the laser that looks like it has been basically melted and re-solidified. And what we're looking for is less laser affected areas and smaller channels. So we want to stay as true to the original geometry of the polymer as possible. The other important thing is more qualitative observations. So I want to make sure I avoid anything catching on fire. Any kind of safety concerns like that would make this really unusable in industry. So it really wouldn't be applicable in many larger scale spaces. And also taking a look at how much metal is deposited. So for example, with the glass fiber filled nylon and PLA, we see a much more significant amount of metal being deposited and remaining on the surface versus the PLA and the carbon fiber ABS, which looked more like a spray of material versus a bead or a ball of feedstock that has been melted and resolidified.
Oh, okay. Thanks. Thanks a lot. That was a very nice presentation. I enjoyed it. Thank you.
Thank you.
So Rebecca, there seems to be interest in the metal forming work that you've done. So maybe if you could say a little bit about metals, and since we're getting a new metal laser machine, additive fabrication machine, that would be kind of nice.
Sure. I think Ying Tao had a question first, and then I'd be happy to talk about. I can talk about that all day long.
Sure. Very good work. My understanding is the purpose for this work is provide the support structures for DD, right? So have you considered using low melting temperature metals to provide the supporting structures, not the polymers? I'm assuming the ABS or PEEK, these polymers, the melting temperature is lower than some of these low melting temperature metals like tin or maybe lead. I'm just curious, what is the thoughts behind choosing certain materials?
Yeah, that's a really good point. I think one of the issues that's not actually an issue with this research is it's a pretty new space. No one's really done a lot with support structures in DED. So there's a bunch of different materials that I could try, but I do also want to graduate at some point. So that's always the give and take. I think with lower temperature materials, there's a couple of things to consider. One is the printability of those lower temperature metals. So if you're looking at something like aluminum, if you want to 3D print with aluminum, you have to print in an inert environment. Aluminum does not react well in an open air space. And the system that I'm using does not have inert capabilities, and a lot of DED systems do not have inert capabilities. So it'd be much trickier to print with that material. And I think the other thing is support removal. So one of the nice things about polymers is that, first of all, what we found with the research is that the metal is very, very easy to remove. I mean, when I print these parts, if I accidentally tilt the substrate too much, the metal will just fall off. So ease of removal is a big deal. And even if it turns out that we did have to machine away the polymer, machining polymer is significantly easier, takes less energy, and you are less likely to ruin your machine or break your machine, machining away polymer versus metals. So I think those are my two big considerations with the low temperature metals.
Great. My other question is, I think you mentioned that the nerdy environment. So for the current machine, are you able to print in a nerdy environment so the polymers may not catch on fire like the nitrogen environment?
Yeah, that's a really good point. I did consider that. So my system, I do not have the ability to make an inert environment. That was a consideration. We do have one system at Oak Ridge that can print in an inert environment, but it can't print with polymers. So when I discussed this thoroughly with the safety engineers at the lab beforehand, and we decided to run the initial trials on very small samples of polymer. So in case there was any kind of burning of the polymers, that there wouldn't be a lot of material. But after running those initial trials, we basically determined the power limits that we could use. So I mentioned that I print at 100 watts. Usually when we print metal on metal, we're running more on the order of 500 to 750 watts. So we're lowering our power significantly. And we have determined that that is fairly safe. It would definitely be better if we could print in an inert environment, but the system that I'm using that has both polymer and metal capabilities is unfortunately not also equipped with an inert environment.
Great. Thank you very much.
Yeah, thank you.
Rebecca, I happen to be a good friend of your dad, and I know that that has nothing to do with your seminar. For more than 30 years now, we were graduate students in and about the same time, and I've been meeting at NAMRAC, and these are all topics we possibly know, NAMRAC and MSAC and so on. for several years. I just have a question for you. Are you open to conversing possibly on a separate level with me? We would like to kind of talk to you about some work that you could be a great part of with what we're doing. So if I could contact you directly, I would appreciate it. I have your email address. Would that be a good way to get in touch with you?
Yeah, I check. If it's my ORNL email, I check that every day. So that is a great way to get in touch with me.
So I should get with you in the next couple of days. I'm hoping to. And John Antonio, he was supposed to be here. Maybe he's in some other meeting. But John and I have talked about this a little bit. So maybe it would be great for us to communicate for a few minutes.
Yeah, that would be great. I'm looking forward to it.
Thank you so much. Really loved your seminar. Enjoyed your conversation. Enjoyed the research. Thank you so much.
Thank you. I appreciate it. I do. I really like this research, so I'm always happy to talk people's ear off about it.
No, that's good. That's good. Excellent. Thanks, Professor Mistry and the graduate committee for inviting me for this seminar. It's been really, really wonderful. Thank you.
Continue, Rebecca.
Yes. Were there any more questions about this research? If not, I'm just kind of curious, what type of system are you getting in? Is it SLM, selective laser melting, or does it work with an electron beam or something different?
The machine we are getting is a concept laser series 5 from GE. So it's a power by diffusion and selective laser melting for metal 3D printing system. So we already have the contract in hand, and the machine will be installed probably in next January. The latest probably the March. It depends on the lab preparation. So we are very happy to see we can have a metal machine on campus, and the university is growing the research in this direction very hard. And we also have multiple faculty working on the 3D printing of polymer and fiber-reinforced composites. So we can see a lot of potential collaborations in different directions on metals, on polymers, on composites. We are very happy to work with you and other people at Outreach.
Yeah, that sounds great. No, because I'm doing my my PhD in metals, and I did my master's in polymers. And I guess my PhD is more of an intersection between polymers and metals. So I have a lot of interest in dipping my toes in all sorts of additive manufacturing research. Do you have any idea what you're going to be using the system for once it gets in?
The first material we're going to use is titanium 64 grade 23. So it's an aerospace and a bio compatible materials, can be used both for aerospace and the biomedical applications. So we are very excited to start working on these materials, and hopefully it will start new research fields for the whole school and for the whole college. But the machine can be also used for other metals like steel or aluminum, copper, Inconel. There's if we get materials from GE, there's more than 10 different materials we can choose from. But the machine, we also get license from GE. We got permission to open the entire printing parameter set, so we can use the machine to develop other new materials for additive manufacturing, especially metals.
That's really cool. Yeah, I know that titanium is a really exciting metal to use with the SLM processes, because you can do the inert space, and there's so many applications, like you said, with the biocompatibility, so with any kind of implants and with aerospace. But it is nice to be able to use multiple different materials on the system.
Exactly. And the machine is open to the whole college or the whole university. So anyone on campus can use it. We're very happy to open the machine to everybody. So it's not only for AME or ISC. So any faculty on campus are welcome.
I think also, I would like to add that local industry who would be interested, it's kind of going to be a shared model where even industry can get some space and time with the equipment. And it is put at a very strategic location so that, it's not going to be it's very easy access to the highway. So industry can come in, and a lot of aerospace and defense businesses can come in, and of course, Air Force wants to have a hand on it also, since they have exact same system. Tinker has exactly the same system, so that's why they wanted us to buy this. They upgraded the system for us, meaning we didn't ask for the second laser, the two laser system, but it just ended up that way.
Oh, that's great. No, I know, because I know cost is a pretty big barrier with these systems, especially the ones that can make and use parts. So opening it up to industry is a really great opportunity for local industries in the area.
Yeah, I think, and also we have a health sciences center here. I mean, I can't talk, you know, I have to say some great things. We have an excellent campus here, OU Health Sciences Center. And what they have been wanting one of these machines for a very long time. And for not because of the money aspect of it, but they have a big operational, you know, mind block right now that they feel that some engineers have to operate it. So this will increase the collaborations with especially the College of Dentistry. You know, they are making dental implants. They're making a lot of, you know, we in the past several years we printed something, an electron beam melting machine with some other private company, the mandible and maxilla and parts of the human skull. But you know, with Ti-64, we use Ti-64. We use porous scaffolds of that. So they've been wanting to do something like that. And they wanted to try and experiment this whole SLS and these kind of processes. So College of Dentistry, College of Allied Health and Public Health, they're all very interested. And also medicine, College of Medicine is very interested. So there is going to be a lot of access to several people, which makes it, you know, makes it excellent to have a metal printer. This is the first metal printer on campus, big metal printer on campus.
Yeah, that's great. That's a really impressive collaboration of a bunch of different disciplines, right, which is so cool to see with engineering. I really like to see when my research or any engineering research can be applied in multiple different fields. That's really an exciting opportunity.
I think the biomedical engineering school, with the opening of the biomedical engineering school, you know, the door has opened to Health Sciences campus. So they are doing a lot of collaborative work with us. And this just bolsters that relationship a little bit further.
Rachel?
Well,
Actually,
okay.
I'm sorry, I had a quick question, maybe a couple of them regarding the presentation.
Yeah, of course.
So you're talking about the polymer, the substrates. So did you choose them based on any parameters, or were they like selected on like the availability to you?
Yeah, so availability was one factor. Just because I wanted to make sure that any support structure that we chose as a recommendation for use in industry would be available, readily available for purchasing and for use on a system. In general, the 5 polymers I selected 2 different types of fillers. So I wanted to test carbon fibers and I wanted to test glass fibers. I wanted to test at least one low temperature unfilled polymer just to see if that was even feasible as a support, because if it was, then PLA is easy to print on any system. It's the material you get with desktop 3D printers when you buy them from Amazon. So if that was a potential for a support structure, I wanted to find that out early on in the research. So it did, yes, there was some looking into the availability. Not in the sense of I just looked around my lab and grabbed whatever was there, but in the sense of how available are these for purchase and how expensive are they. But there was also printability considerations. So I did test one high temperature polymer, but even if that had worked better than it did, I likely wouldn't recommend it for widespread use because printing with PEEK is much more complicated than printing with the lower temperature ABS and PLA materials. And then additionally, the temperature on my system only goes up to 300 C. So I cannot print materials that have printing temperatures above that. So actually for the high temperature peak material, I had to get that printed on a different system and then put it in the system that I use. So yes, like you said, there was some consideration to availability, but there were other aspects that I considered as well.
Okay, sorry, just a follow-up question to that. So you said you wanted to try out the carbon and glass fibers. So is there any specific reason to just try the fibers, or like, do you think there can be some useful nanocomposite polymer, like nanocomposites in this field as well?
I definitely think there could be an application. Again, the reason I selected the fiber-filled composites is because they're pretty readily available. So you can go online and purchase the carbon fiber-filled feedstock material. And also because there's a lot of expertise that's readily available on printing with the fiber-filled polymers. To my knowledge, there's a little bit less work done with the nanocomposites. I did also look into printing with metal powder embedded polymers, but those are a little bit less readily available. So I haven't been able to find them in print substrates yet. So yeah, I think that could definitely be a good option to test. I just think it's a little bit less readily available if we want to bring these support structures up to a bigger, more industry level scale.
Okay, thank you so much for that. Actually, so in our lab, we are working on some polymer nanocomposites, and like that, this sounds like a really good application we could try to work on in the future.
Yeah, what kind of nanocomposites are you working on?
So right now we are working on polymer and graphene composites.
Okay, yeah, graphene could definitely be very interesting. What percentage graphene versus polymer are you looking at?
I mean, so we are actually focusing on getting high thermal conductivity. So at this point, maximum we have gone up. I mean, maximum as in we are focusing on achieving high thermal conductivity at lower weight percentages. Mm-hmm. So we have gone up to like, let's say 10 to 15 weight percentages max at this point.
Okay. Actually, that's a really interesting point, because one feature of support structures in metal 3D printing it's more commonly seen in SLM printing is they use the support structures not only to support geometries, but to support large thermal gradients in the print. So they're used to deal with heat inequalities, is the wrong word, heat gradients, and reduce those. So I think if you had a highly thermally conductive polymer that you could use as a support, that would be very interesting.
Okay, yeah, thank you so much for that. I mean, yeah, actually we are actually now focusing on the 3D printing of those polymer composites as well. Mm-hmm. So maybe we can see if something works out in this direction.
Yeah, definitely keep me updated. I think that sounds really applicable to the work I'm doing.
Yeah, thank you so much.
Yeah, thank you.
Okay, any further questions for Rebecca from anybody? Okay, then I guess I will close this out. Thank you everybody so much for attending this seminar. We will be uploading the recording of this on our YouTube channel later. If you would like to get in contact with Rebecca or with any of us, just please email us or Rebecca. And I guess that's all we have for today. So thank you so much.